Section. Introduction. We're going to talk about large unsupervised language models, or LMs, which are trained on vast amounts of data. These models learn from a wide range of human-generated data, which can be both a strength and a weakness. For instance, while we want our AI coding assistant to understand common programming errors to correct them, we don't want it to replicate these mistakes when generating code. We want it to lean towards the high-quality coding skills found in its training data, even if they are rare. Similarly, if half the population believes in a common misconception, we want our language model to be aware of it, but not to present it as a fact half the time. So, it's crucial to carefully select the model's responses and behavior from its vast knowledge and abilities to create AI systems that are safe, efficient, and controllable. Existing methods typically guide LMs to align with human preferences using reinforcement learning, RL. However, we'll demonstrate that the RL-based objective used by these methods can be optimized with a simple binary cross-entropy objective, which greatly simplifies the preference learning process. Existing methods instill desired behaviors into a language model using curated sets of human preferences that represent safe and helpful behaviors. This preference learning stage happens after an initial stage of large-scale unsupervised pre-training on a large text dataset. While the most straightforward approach to preference learning is supervised fine-tuning on human demonstrations of high-quality responses, the most successful methods use reinforcement learning from human or AI feedback. These methods fit a reward model to a dataset of human preferences and then use RL to optimize a language model policy to produce high reward responses without straying too far from the original model. While these methods produce models with impressive conversational and coding abilities, they are more complex than supervised learning and require training multiple LMs and sampling from the LM policy during training, which incurs significant computational costs. In this paper, we propose a new method called direct preference optimization, DPO, which directly optimizes a language model to adhere to human preferences, without explicit reward modeling or reinforcement learning. DPO increases the relative log probability of preferred to dispreferred responses, but it includes a dynamic, for example importance weight that prevents the model from degenerating. Like existing algorithms, DPO relies on a theoretical preference model that measures how well a given reward function aligns with empirical preference data. However, DPO defines the preference loss as a function of the policy directly, rather than using the preference model to train a reward model and then train a policy that optimizes the learned reward model. Given a dataset of human preferences over model responses, DPO can optimize a policy using a simple binary cross-entropy objective, without explicitly learning a reward function or sampling from the policy during training. Our main contribution is DPO, a simple RL-free algorithm for training language models from preferences. Our experiments show that DPO is at least as effective as existing methods, including PPO-based RLHF, for learning from preferences in tasks such as sentiment modulation, summarization, and dialogue, using language models with up to 6 billion parameters. Self-supervised language models of increasing scale can complete some tasks zero-shot or with few-shot prompts. However, their performance on downstream tasks and alignment with user intent can be significantly improved by fine-tuning on datasets of instructions and human-written completions. This instruction tuning procedure enables LMs to generalize to instructions outside of the instruction tuning set and generally increase their usability. Despite the success of instruction tuning, relative human judgments of response quality are often easier to collect than expert demonstrations. Thus, subsequent works have fine-tuned LMs with datasets of human preferences, improving proficiency in translation, summarization, storytelling, and instruction following. These methods first optimize a neural network reward function for compatibility with the dataset of preferences under a preference model, then fine-tune a language model to maximize the given reward using reinforcement learning algorithms. A closely related line of work leverages LMs fine-tuned for instruction following with human feedback to generate additional synthetic preference data for targeted attributes such as safety or harmlessness, using only weak supervision from humans in the form of a text rubric for the LLM's annotations. Despite the appeal of using relative human preferences, fine-tuning large language models with reinforcement learning remains a major practical challenge. This work provides a theoretically justified approach to optimizing relative preferences without RL. Outside of the context of language, learning policies from preferences has been studied in both bandit and reinforcement learning settings, and several approaches have been proposed. However, in the context of learning from human preferences, we typically learn from a fixed batch of offline preference annotated action pairs. Various algorithms for preference-based RL exist, but they generally involve first explicitly estimating the latent scoring function, i.e., the reward model, and subsequently optimizing it. We instead present a single-stage policy learning approach that directly optimizes a policy to satisfy preferences. Section Summary. Large unsupervised language models, LMs, trained on vast datasets have impressive capabilities, but their behavior may not always align with desired preferences. Existing methods use reinforcement learning, RL, to steer LMs towards human preferences, but this approach is computationally expensive. In this paper, we propose a simpler algorithm called direct preference optimization, DPO, that directly optimizes a language model to adhere to human preferences without explicit reward modeling or RL, achieving comparable results to existing methods. Section. Preliminaries. Let's break down the complex process of reinforcement learning from human feedback, RLHF, into simpler terms. This method is commonly used in various studies and consists of three main stages: supervised fine-tuning, preference sampling and reward learning, and reinforcement learning optimization. In the first stage, supervised fine-tuning, we start with a general pre-trained language model. We then fine-tune this model using supervised learning on a high-quality dataset. This dataset is related to the specific tasks we're interested in, such as dialogue, summarizing, and so on. The result of this stage is a fine-tuned model. The second stage is preference sampling and reward learning. Here, we use the fine-tuned model to generate pairs of answers to prompts. These pairs are then shown to human labelers, who indicate their preferred answer. We assume that these preferences are generated by a hidden reward model, which we don't have direct access to. To model these preferences, we often use the Bradley-Terry model, which suggests that the human preference distribution can be expressed as the ratio of the exponential of the reward for each answer. Next, we use a dataset of comparisons to estimate the parameters of a reward model. We frame this as a binary classification problem and calculate the negative log likelihood loss. In the context of language models, we often add a linear layer on top of the final transformer layer of the fine-tuned model to predict the reward value. To ensure a reward function with lower variance, we normalize the rewards. The third stage is reinforcement learning optimization. Here, we use the learned reward function to provide feedback to the language model. We formulate an optimization problem where we aim to maximize the expected reward while minimizing the deviation from the initial fine-tuned model. This constraint is important as it prevents the model from deviating too far from the distribution on which the reward model is accurate, and it also maintains the diversity of the generated answers. However, due to the challenges of applying reinforcement learning algorithms on large-scale problems such as fine-tuning language models, we propose a simpler approach for policy optimization using preferences directly. This approach, which we call direct preference optimization, DPO, bypasses the reward modeling step and directly optimizes a language model using preference data. We leverage an analytical mapping from reward functions to optimal policies, which allows us to transform a loss function over reward functions into a loss function over policies. In essence, the policy network represents both the language model and the reward. We start with the same reinforcement learning objective as previous work, under a general reward function. We then rearrange the equations to express the reward function in terms of its corresponding optimal policy, the reference policy, and the unknown partition function. We can apply this reparameterization to the ground truth reward and corresponding optimal model. The optimal RLHF policy under the Bradley-Terry model satisfies the preference model, which we can express in terms of only the optimal policy and reference policy. Now that we have the probability of human preference data in terms of the optimal policy rather than the reward model, we can formulate a maximum likelihood objective for a parameterized policy. This way, we simultaneously bypass the explicit reward modeling step while also avoiding the need to perform reinforcement learning optimization. The DPO update increases the likelihood of the preferred completions and decreases the likelihood of dispreferred completions. Importantly, the examples are weighed by how much higher the implicit reward model rates the dispreferred completions, scaled by a parameter, i.e., how incorrectly the implicit reward model orders the completions, accounting for the strength of the constraint. The general DPO pipeline is as follows. 1. Sample completions for every prompt, label with human preferences to construct the offline dataset of preferences, and 2. Optimize the language model to minimize the DPO loss for the given reference model and dataset and desired parameter. In practice, one would like to reuse preference datasets publicly available, rather than generating samples and gathering human preferences. Further details related to the implementation and hyperparameters can be found in the appendix. Section Summary. The RLHF pipeline consists of 3 phases: supervised fine-tuning, preference sampling and reward learning, and reinforcement learning optimization. In the supervised fine-tuning phase, a pre-trained language model is fine-tuned on a high-quality dataset for the downstream task of interest. In the preference sampling and reward learning phase, the fine-tuned model is prompted with inputs to generate pairs of answers, which are then presented to human labelers who express preferences for one answer. These preferences are used to estimate a reward model. In the reinforcement learning optimization phase, the learned reward function is used to provide feedback to the language model, and the model is optimized using preference data directly, bypassing the explicit reward modeling step. Section: Theoretical Analysis of DPO. In this section, we're going to delve deeper into the DPO method, providing a theoretical explanation and highlighting its advantages over actor-critic algorithms used for RLHF, such as PPO. The DPO method is unique in that it can learn the policy using a single maximum likelihood objective, bypassing both explicit reward estimation and RL. This optimization objective is equivalent to a Bradley-Terry model with a specific reward function. This function is the ratio of the probability of an event under our model to the probability of the same event under a reference model, all multiplied by a constant beta. We optimize our model in the same way as we would optimize the reward model in the Bradley-Terry model. We're going to build the theory behind this reparameterization, showing that it doesn't limit the class of learned reward models and allows for the exact recovery of the optimal policy. We start by defining an equivalence relation between reward functions. 2 reward functions are equivalent if the difference between them is a function of the input. This equivalence relation divides the set of reward functions into classes. We can then state 2 important points. First, under the Plackett-Luce preference framework, 2 reward functions from the same class induce the same preference distribution. Second, 2 reward functions from the same equivalence class induce the same optimal policy under the constrained RL problem. There is a well-known issue with the Plackett-Luce family of models, which is under specification. Because of this, we usually need to impose additional constraints to get any guarantees on the maximum likelihood estimates. However, all reward functions from the same class yield the same optimal policy, so we're only interested in recovering an arbitrary reward function from the optimal class. Under certain assumptions, all reward classes consistent with the Plackett-Luce models can be represented with our reparameterization. To prove this, consider any reward function, which induces a corresponding optimal model. We can show that a reward function from the equivalence class of this function can be represented using our reparameterization. We define a projection function that normalizes the reward function with the logarithm of the partition function of the optimal model. This projection function produces a member of the equivalence class of the original reward function with the desired form, and we don't lose any generality in our reward model from the proposed reparameterization. We can also view this theorem as specifying exactly which reward function within each equivalence class the DPO reparameterization selects. This is the reward function that satisfies the condition that the sum of the probabilities of all events under the reference model equals 1, meaning it's a valid distribution. However, we can see that this sum is the partition function of the optimal policy induced by the reward function. The key insight of the DPO algorithm is that we can impose certain constraints on the under-constrained Plackett-Luce family of preference models, such that we preserve the class of representable reward models, but explicitly make the optimal policy analytically tractable for all prompts. Section Summary. In this section, the authors provide a theoretical analysis of the DPO method and its advantages over actor-critic algorithms. They explain that the optimization objective of DPO is equivalent to a Bradley-Terry model with a reward function, and they show that all reward classes consistent with the Plackett-Luce and Bradley-Terry models can be represented using a specific reparameterization. This reparameterization allows for the exact recovery of the optimal policy and ensures that the optimal policy is analytically tractable for all prompts. Section: Instability of actor-critic algorithms. We're going to delve into the instability of actor-critic algorithms, specifically those used for reinforcement learning from human feedback, RLHF, such as proximal policy optimization, PPO. We'll be using our framework to identify these instabilities. Our focus is on the RL fine-tuning step, which is a part of the RLHF pipeline. We'll be drawing parallels to the control as inference framework for the constrained RL problem. We start by assuming a parameterized model, which we'll denote as pi_theta, that depends on y given x. We aim to minimize the Kullback-Leibler, KL, divergence between this model and the optimal policy, denoted as pi_star, which is induced by the reward function r_phi. After some algebraic manipulations, we arrive at an optimization objective. This objective is to maximize the expected value of the logarithm of the ratio of pi_theta to a reference policy, denoted as pi_ref, under pi_theta. This is the same objective that has been optimized in previous works using the DPO equivalent reward for the reward class of r_phi. In this context, we can interpret the normalization term in the function f as the soft value function of the reference policy pi_ref. While this term doesn't affect the optimal solution, its absence could lead to high variance in the policy gradient of the objective, making learning unstable. We can account for this normalization term using a learned value function, but this can also be challenging to optimize. Previous works have normalized rewards using a human completion baseline, which is essentially a single-sample Monte Carlo estimate of the normalizing term. In contrast, the DPO reparameterization provides a reward function that doesn't require any baselines. Now, let's move on to the experiments. We'll be evaluating DPO's ability to train policies directly from preferences. We'll start with a controlled text generation setting and ask, how efficiently does DPO balance maximizing reward and minimizing KL divergence with the reference policy, compared to common preference learning algorithms like PPO? We'll then evaluate DPO's performance on larger models and more challenging RLHF tasks, including summarization and dialogue. We find that DPO tends to perform as well or better than strong baselines like RLHF with PPO, with minimal tuning of hyperparameters. It also performs well in returning the best of n-sampled trajectories under a learned reward function. Our experiments involve 3 different open-ended text generation tasks. In controlled sentiment generation, the policy must generate a positive sentiment text given a prefix of a movie review from the IMDb dataset. For summarization, the policy must generate a summary of a forum post from Reddit. In single-turn dialogue, the policy must produce an engaging and helpful response to a user's query. We use 2 different approaches to evaluate our experiments. In the controlled sentiment generation setting, we evaluate each algorithm by its frontier of achieved reward and KL divergence from the reference policy. However, in real-world scenarios where the ground truth reward function is not known, we evaluate algorithms based on their win rate against a baseline policy. In addition to DPO, we also evaluate several existing approaches to training language models to adhere to human preferences. These include zero-shot prompting, supervised fine-tuning, and unlikelihood. We also consider PPO using a reward function learned from the preference data and PPO-GT, which learns from the ground truth reward function. Finally, we consider the best of n baseline, which samples n responses and returns the highest scoring response according to a learned reward function. Section Summary. The section discusses the instability of actor-critic algorithms and introduces the DPO framework as a solution. It also presents experimental evaluations of DPO's performance in various text generation tasks, comparing it to other algorithms such as PPO and preferred FT. The evaluation methods include analyzing the frontier of achieved reward and KL divergence, as well as win rate against a baseline policy using GPT-4 as a proxy for human evaluation. Section. How well can DPO optimize the RLHF objective? We're interested in understanding how well DPO, or diverse policy optimization, can optimize the RLHF, or reward learning from human feedback, objective. In typical RLHF algorithms, there's a balance between maximizing rewards and ensuring the policy doesn't deviate too much from the reference policy. This is achieved through a KL-constrained reward maximization objective. When we compare different algorithms, we need to consider both the rewards achieved and the KL discrepancy. A slightly higher reward with a much higher KL discrepancy isn't necessarily a good thing. We've run multiple training sessions for each algorithm, adjusting the policy conservativeness for each run. For example, for PPO, or proximal policy optimization, we use target KL values of 3, 6, 9, and 12. For unlikelihood, we used beta values of 0.05, 0.1, 1, and 5, and alpha values of 0.05, 0.1, 0.5, and 1. We also used random seeds for preferred FT. In total, we ran 22 training sessions. After every 100 training steps, we evaluated each policy on a set of test prompts. We calculated the average reward under the true reward function and the average sequence level KL with the reference policy. We found that DPO was the most efficient, achieving the highest reward while maintaining a low KL. This is significant for a few reasons. Firstly, DPO and PPO optimize the same objective, but DPO is more efficient. Secondly, DPO performs better than PPO, even when PPO has access to ground truth rewards. Next, we wanted to see if DPO could scale to real preference datasets. We evaluated DPO's fine-tuning performance on summarization and single-turn dialogue. For summarization, we found that automatic evaluation metrics, like Rouge, don't always correlate well with human preferences. We evaluated different methods by sampling completions on the test split of the TLDR summarization dataset and calculating the average win rate against reference completions in the test set. We found that DPO had a win rate of about 61% at a temperature of 0.0, which was better than PPO's 57% at the same temperature. DPO also achieved a higher maximum win rate compared to the best of N baseline. We also compared DPO and PPO in human evaluations. DPO samples at a temperature of 0.25 were preferred 58% of the time over PPO samples at a temperature of 0. We evaluated different methods on a subset of the test split of the Anthropic HH dataset with one step of human-assistant interaction. We found that DPO performed as well or better for the best performing temperatures for each method. In conclusion, DPO is the only computationally efficient method that improves over the preferred completions in the Anthropic HH dataset. It provides similar or better performance to the computationally demanding best of 128 baseline. DPO also converges to its best performance relatively quickly. Section Summary. The section discusses the optimization of the RLHF objective in DPO and compares it with other algorithms. It shows that DPO achieves the most efficient trade-off between reward and KL discrepancy, outperforming PPO and even PPO with access to ground truth rewards. DPO also performs well in fine-tuning tasks for summarization and single-turn dialogue, surpassing PPO in win rates and demonstrating robustness to sampling temperature. Overall, DPO is computationally efficient and provides similar or better performance compared to other baselines. Section. Validating GPT-4 judgments with human judgments. We carried out a study involving human participants to validate the judgments made by GPT-4. This was done using the outcomes of the TLDR summarization experiment and two different prompts for GPT-4. One prompt was simple, asking which summary better encapsulates the key information in the post. The other prompt was concise, asking which summary is more succinct. We chose to evaluate the concise prompt because we noticed that GPT-4 tends to prefer longer, more repetitive summaries than humans do when using the simple prompt. We made 3 comparisons, using the highest, lowest, and a middle performing method, with the goal of covering a range of sample qualities. All 3 methods were compared against a method that samples greedily from PPO, its best performing temperature. We found that GPT-4 tends to agree with human judgments as often as humans agree with each other, suggesting that GPT-4 could be a good stand-in for human evaluations. In general, the concise prompt from GPT-4 provides win rates that are more representative of human judgments. Therefore, we used this prompt for the main results in the section. For more details about the human study, including the web interface shown to raters and the list of human volunteers, see the appendix. Learning from preferences is a powerful and scalable framework for training capable, aligned language models. We have introduced DPO, a simple training paradigm for training language models from preferences without the need for reinforcement learning. DPO identifies a connection between language model policies and reward functions that allows for training a language model to meet human preferences directly. This is done with a simple cross-entropy loss, without the need for reinforcement learning or loss of generality. DPO performs similarly or better than existing RLHF algorithms, including those based on PPO, with virtually no tuning of hyperparameters. This significantly lowers the barrier to training more language models from human preferences. Our study raises several questions that are beyond the scope of the current study. For example, how does the DPO policy generalize out of distribution, compared with an explicit reward function? Can training with self-labeling from the DPO policy make effective use of unlabeled prompts? How does reward over optimization manifest in the direct preference optimization setting? While we evaluate models up to 6B parameters, exploring the scaling of DPO to state-of-the-art models orders of magnitude larger is an exciting direction for future work. We also found that the win rates computed by GPT-4 are influenced by the prompt. Future work may study the best way to elicit high-quality judgments from automated systems. Finally, DPO has many potential applications beyond training language models from human preferences, including training generative models in other modalities. We would like to acknowledge the funding from a Knight Hennessy Graduate Fellowship, CIFAR Fellows, the Stanford Accelerator for Learning, SAL, Stanford Institute for Human-Centered Artificial Intelligence, HI, Generative AI for the Future of Learning Seed Grant Program, and ONR Grant NO0014-201-2675. The Stanford Center for Research on Foundation Models, CRFM, provided part of the compute resources used for the experiments in this work. All authors contributed significantly to the design, analysis, and iteration of experiments, writing and editing the paper, and managing the project's progress.